Okay, everybody, welcome back. All right. A little bit of a late start here. Had some technical problems. We're having some electrical issues here. Power went out last night. Anyway, let us continue. I have everything graded that's been turned in. You'll see now that these other chapters we're going to be really spread out. So we're, like I said earlier in the semester, we're going to probably end up at one or two what I call it study sessions. In other words, I'm here, but we're not lecturing. Open up to whatever questions, what questions concerning the chapters and getting you ready for the final exam. So, all right, so let us continue with chapter. Any questions, comments, concerns? All right, well, let us continue. We ended up on slide 14, and we've been talking about chemical reactions, okay? And this one here is called a combustion reaction. Now, the important aspect about a combustion reaction, which you just got to remember, is point number one. We're going to do combustion reactions of only hydrocarbons. And so here we got propane, and here's the general formula for hydrocarbons, which is a compound which consists of nothing but carbon and hydrogen, very non-polar species, okay? And one of the ingredients, the necessary ingredient or reactant for any combustion reaction, obviously, is oxygen. Sometimes people tend to forget that that's a requirement. So we can very quickly, you can be given a question like write the combustion reaction of propane gas, and then they give you the formula, okay? And so we can write that down. We know that here's the formula because that's given for propane. And obviously, oxygen is required for this propane to burn. Okay, without oxygen, nothing will burn. You will not get a flame right here with no oxygen. Now, that's point number one was hydrocarbon. Point number two was oxygen is a reactant. Point number three is this, for Chem 130, I repeat, for Chem 130, a combustion of any hydrocarbon in the presence of oxygen will only give you two products. That's it. Okay. One of them is carbon dioxide, and the other one is water. All right. All right. So that's and everything's burning. So everything's in the gas phase. There are some hydrocarbons that are larger number of carbons. Around 6 carbons, and then they start becoming liquidy. But below that, they're gases. So we have propane gas, obviously, and oxygen gas, okay, and carbon dioxide, and also a gas, and water, which because it's burning and it's hot enough to boil water, it's also will be in the gas phase. Okay. So everybody's in a gas phase, and that is the equation for the combustion of a hydrocarbon to in the presence of oxygen to produce carbon dioxide and water. Now, how to balance these for hydrocarbon or for combustion reactions? We balance them first, starting with carbon. All right. So we look at the reaction. We got 3 carbons over here, but we only have 1 carbon over here on the right side. So 3 carbons in reactant, 1 is a product. So what do? We simply just put a 3 in front of carbon dioxide, and that picks up our carbon content. So now carbons are balanced. Okay. Second is we balance the hydrogens. Okay. So notice on the left side, the reactant side, there are 8 hydrogens, whereas on the right side, we have 2 hydrogens. I'm going to put it. we have 2 hydrogens on the product side and 8 on the reactant side. So 9 times out of 10, it's a real simple thing of adding a half of the hydrogens of the reactant side to the number, the coefficient on the product side of water. So if we put a 4 in front of water as a coefficient, that gives us 8 hydrogens. So now the hydrogens are balanced, carbon is balanced, okay, we're good to go. And then finally, we balance the oxygens, okay? So we need to combine all of the oxygens. And on the reactant side, there's only 2 oxygens. And I write them down just to assist me in making sure that I'm, keeping inventory of all the atoms and then making sure things are balanced out. So I write it down, 2 oxygens on the left-hand side. And then on the right-hand side, we have 6 hydrogens coming from carbon dioxide in the form of carbon dioxide. Right? We got 3 molecules of carbon dioxide. Each molecule of carbon has 2 oxygens, so it's a total of 6. In the form of water, we have 4 oxygens. So we have a grand total of 10 oxygens in the product side. Okay. 6 is carbon dioxide, 4 as water. So now taking that number, which should be divisible by 2, and just take half of it, and we put a 5 in front of oxygen on the reactant side. And what that does is that picks up our oxygen content to 10. And so now we have a balanced chemical reaction. We have 1 propane requires 5 molecules of carbon dioxide, and it yields 3 molecules of carbon. What did I say? My mistake. 1 molecule of propane requires 5 molecules of oxygen, which produces 3 molecules of carbon dioxide and 4 molecules of water. Okay. You can see here that one propane, takes up quite a bit of oxygen. 5. Imagine if now what happens when you increase the carbon content to larger numbers, that number goes up. So we actually require a lot more oxygen to burn these larger hydrocarbons, which then produces a lot more carbon dioxide. And now we have a challenge with respect to carbon dioxide emissions, and that concentration goes up. Which in the past wouldn't be a problem because their greenery would handle carbon dioxide, because obviously, plants need the carbon dioxide, but their quantity is decreasing, so posing a bit of a problem. All right, so here's the reaction we just wrote, and then here's the balanced chemical equation, okay? All right, so combustion reactions, the points we had just talked about is we're only going to do with simple hydrocarbons. As far as balancing, do the carbon first, followed by the hydrogen, then at the last is the oxygens. And remember that oxygen is always a reactant. Okay. All right, so being the case, telling you what happens with respect to hydrocarbons, the combustions of hydrocarbons, you should be able to predict and state what the products are. And from that information, what the reactants needed, you can write a chemical reaction for that. Then given the process of balancing, you should be able to balance that chemical reaction for combustion reactants, okay? All right, so these we talked about in the acid-base chapter, and the acid-base neutralization reaction, where we have a acid, which again, by definition, remember, an acid is any species that produces the proton, H+, in the presence of a ionic compound, which is a hydroxide. Based on the definition of base, Arrhenius base is any species that produces a hydroxide ion, okay? Well, the proton and the hydroxide combine to form what? H2O. And then we have the corresponding salt of whatever the metal was here with the hydroxide combining with whatever the anion was from the acid to form its particular salt. Okay. Remember, the term salt does not necessarily pertain to sodium chloride. No, salt is any ionic compound, which by definition is a combination of a metal and a non-metal. Okay. All right, so the takeaway from here is this: hope one, recognize that you're dealing with an acid, and as we were talking about this, first of all, you have an covalent compound, HA, which, due to the nature of the beast, being an acid, it is the only covalent compound that will dissociate when placed into an aqueous solution. Okay? And in dissociating, then that is what's happening uh, with respect to generating a proton. All right, so we have written H first, 9 times out of 10. You got hydrogen written first in the formula. Good deduction that you're dealing with an acid. Okay. So what I would do here in the beginning to get comfortable with it is the fact is break them into the ions. Okay. We got hydrogen and we're going to get the chloride. Okay. When we put HCl in solution. Now we also know that barium hydroxide will produce the barium 2 ion and 2 hydroxides. Okay. 2 hydroxides. So breaking them down into ions will also help me when I put them together again to write the correct salt that is generated. Now, with respect to proton and hydroxides, they're going to automatically generate water. They're going to react together and produce water. Now, with respect to acid-base reactions, the best way to balance these is to follow the protons and the hydroxides. Keep it in mind that it takes one proton. One proton needs one hydroxide in this reaction, okay, to produce one water. So if you follow the protons and hydroxides to produce the correct number of water molecules, and then you have the ions of the corresponding salt set up, you can recombine them, and what happens by default, you have a balanced chemical equation. All right. So here we're going to produce one proton from HCl and 2 hydroxides. So what that tells you is this: I'm going to need 2 HCl's, 2 molecules of hydrochloric acid, because barium hydroxide is going to produce 2 hydroxides, and I have to add enough HCl to neutralize the OH. So I need 2. Well, that means I got 2 protons is going to react with 2 hydroxides. Guess what? I'm going to make 2 waters, okay, because of this scenario. And if I start off with 100 protons, I need 100 hydroxides, which will give me 100 molecules of water. All right. Okay, so now we're looking at the salt. So we got barium ion, okay, which is +2. So we got the barium ion and then the chlorides. And since we put a 2 in front of HCl, that means we're going to have 2 chlorides, which is perfect because we need 2 chlorides. So the formula for the salt is BlCl2. All right. Now that we've done that, we go back and check. We have a total of 4 hydrogens on the reactant side. We got 2 coming from hydrochloric acid, 2 coming from the hydroxide. On the product side, we have 4 hydrogens coming from 2 molecules of water. So they're good to go. Barium, we got 1 barium on the reactant side, and we have 1 barium on the product side. And then we're going to have 2 chlorides on the reactant side. And sure enough, we got 2 chlorides on the product side. So we have a balanced chemical reaction. Let me clear up my mess. Put that down. So you got two there. Okay. And now, with respect to making water, okay, when you generate water because of the reaction of the proton and hydroxide, you got H2O liquid. So its physical state is liquid. Okay, it's already in an aqueous solution, which is really a crazy thought here, because marketing has really put water into the forefront as far as, you know, all these different types of water. But think about this for a second. There's stores out there, especially all the natural organic products, where they label water as concentrated water. And when I first saw that label, I was like, whoa, okay. Water is already concentrated. You by adding more water to water, you don't make more concentrated water. It's concentrated. It's not gonna get any more concentrated than it is. So save your money. Just concentrated water is not anything special. It doesn't exist. All right. So now, do we have a balanced chemical equation? We just checked. We just checked all the atoms. All right. The second one. All right. So we have phosphoric acid. Okay. All right. Notice the 3. That means 3 protons. Okay. 3 protons being generated. And then we got the phosphate anion. Okay. Then we got calcium, which has a plus 2. And then we're going to generate 2 hydroxide ions. Okay. So, like I suggested, follow the protons and the hydroxides to balance it. We know that we're going to make water. There's no question about it. Question is how many water molecules we're going to make. Okay. Notice we got 3 protons on the left. We got 2 on the right. Guess what? Remember how we've been using that common number? Well, it's no different. We need to find a common number here for the hydroxide and the proton. Okay? And that common number is 6, right? And so if I have 3 hydroxides, and if I have 2 protons, I would get a total of 6 protons, right? Plus 6 hydroxides. And guess what? How many waters is that going to make? Bam, 6. Okay. So my common number is 3 for the hydroxide. So I simply put a 3 in front of the equation, calcium hydroxide. And then I put a 2 in front of phosphoric acid. Okay. All right. So what that does now is that gives me a total of 2 phosphates on the left side and 3 calciums on the right, on 3 calciums. Okay. So knowing what they are, I just, the phosphate is a -3, calcium is a +2. Let's write them over here to refresh your memory. Remember how we did that? Okay, again, we find a common factor. So a common factor is 2 phosphates and 3 calciums, which is, guess what? Which is what we have here by default. So let's write the formula here. And then we need, oh, what am I doing? Nobody caught that? So we have calcium, subscript 3, parentheses, CO4, 2. Okay. And like I stated earlier, by following the protons and the hydroxide when you're going to do your balancing, the cation and the anion, the salts just fall in place. You don't have to do any calculations and follow them through. The numbers go right through. Okay, let's go check. Okay, we say here we got 6 hydrogens on the reactant side for phosphoric acid, and then we have 6 coming in the form of calcium hydroxide. So that's a total of 12 hydrogens, right? Which, guess what? We got 12 hydrogens in the form of water, so they're good. We got 3 calciums, so the calciums check out. We have 2 phosphates here. There's a 2 here. There's 2 phosphates. They check out. We got a balanced chemical equation. Okay. And so the ratio, and when we do the balancing, also make note of the ratio relative to reactants. You know, we got a 2-to-1 ratio. Remember, it's understood to have a 1 in front of it. We don't write a 1, but it's understood it's a 2-to-1 ratio of hydrochloric acid for every 1 molecule of barium hydroxide. With respect to phosphoric acid and calcium hydroxide, it's a 2-to-3 ratio. So for every 2 molecules of phosphoric acid, I need 3 molecules of calcium hydroxide. Then, when that reaction is done, it will produce 1 molecule of calcium phosphate and 6 molecules of water. Okay, 6 molecules of water. So you can see that with respect to hydrochloric acid, phosphoric acid requires more base to neutralize it, okay? All right. Now, this is the single replacement reaction. Okay, I had a question here. Let's go back. The question was, do we have 6? No, there's a total of 12. Let's go back to it. Okay, you have this 6 right here, and then you had, every molecule of hydroxide has 2, and you have 3 of those, so you have a total of 6 hydrogens from calcium hydroxide and 6 coming from the phosphoric acid, which is a grand total of 12 hydrogens. You see that? And over here, you have 6 molecules of calcium hydroxide, water. So you got 12 hydrogens over here. Got it. Okay, no problem. Yeah, you got to be careful when when you check all your atoms. Make sure that you check if you have 2 different reactants or 2 different products. Make sure that you account for all the hydrogens in all the forms. All right. Now, which brings us to single replacement reaction. Now, the way this works is we got a real general equation. First of all, in the activity series, you have, in the periodic table, you have a table below the periodic table, right above the solubility table called activity series. And what that is the listing of metals relative to each other as to which one is more reactive than the other, okay? And so using that table, we're going to be able to predict whether a reaction proceeds. Point number 1, using activities. Point number 2, metals want to be in the most stable state. So the most reactive metal will always strive to be into an ionic state, okay? So in this scenario, what happens is if you look, let's break it down. We have a metal in elemental form, so it's an element. okay? Zero charge on it, equal number of protons and electrons. And then we have a second metal, which is in ionic form, okay? Now, if this reaction proceeds, the metals, be it the metal that's in elemental form, will replace the metal that's in ionic form and regenerate the new ionic compound, which is MX. Notice M was the metal in elemental form. Now M goes into ionic form. And the metal that was in ionic form now gets converted to molecular form or elemental form, okay? All right, and I did mention this, I think, but this type of single replacement reactions, you may have heard of plating. I'm sure you got, you have jewelry that's plated, silver plated, gold plated, chrome. You got a vehicle with lots of chrome, that's chrome plating. That's whatever is plated on, copper plating, whatever metal you see, that started off as an ionic compound and then got placed onto the surface of some material. So that's basically a good analogy for what's occurring here. Two metals, one of them in elemental form, one of them in ionic form, replace each other, okay? And the driving force is the most reactive metal wants to be in the most stable state. The most stable state for all metals is to be in ionic form. Okay, think about this for a second. Why we say that is because remember that metals want to lose electrons, and by losing electrons, now the outer orbital has lost an electron and basically transfer it over to the other metal. Okay, and the more reactive metal is now in the stable state, which is in ionic form. So the way this occurs says that M was a lot more reactive than A, okay? And so the driving force was for M to be in the solid form, okay? And to determine the reactivity, we use the activity series. And so this is how we predict whether this reaction proceeds, because you could be given the scenario where you just have the general reaction like this. And then the question is, well, will this reaction occur? Well, first of all, recognize that you have an element, a metal all by itself in elemental form, and then you have another metal in ionic form. So this is sending you to a single replacement reaction to identify, okay? So question number one you do is you look at the metals, corresponding metals, regardless if they're in ionic form or elemental form. And from that table, determine which is more reactive. So hypothetically, we have the table shows that M is more reactive than A, okay? So that's the first step we do. Which metal is more reactive? Second thing we do, the question we ask ourselves, is the most reactive metal in ionic form? Is the most reactive metal an ionic compound? Okay. If the answer is yes, it's an ionic compound, and we're only worried right now about the reactants. We don't care about the products yet. If the answer is yes, that implies no reaction, okay? Because the most reactive metal is in ionic form, and so therefore nothing's gonna happen. If the answer is no, that implies positive reaction. And we're going to go through the general formula first, and then we're going to do specifics. positive reaction. So in this example, M is more reactive than A. Okay, M and A are hypothetical metal. Okay, so then we ask the question: is the most reactive metal in ionic form? Well, no. The most reactive metal is M. It's in elemental form. So no is the answer, and that means we have a positive reaction, which means that you just exchange positions of the metals. Now, you first have to convert the metal into ionic form, because you could have a +1, no different than we've been doing before, or +2 or +3. So you convert, you know, you're going to make A is going to get converted to the elemental form. And so then you convert the M into ionic form, which is going to be positive X, whatever that charge is. And then you add that with a sufficient number of negative or X formula, which a chloride or any anion, and figure out its charge. Okay, and then at that point, we put them together properly in the correct number of ratios, so we get the formula max, and then we balance it out. Okay. Okay. I think it'll become clear if we do specific ones. Sometimes it's difficult to just generalities with letters and not really see what they are. So here's the activity series. Okay, it's on the periodic table. You'll see the first set, the first 1, 2, 3, 4, 5, and 6. Those are the most reactive metals. They are so reactive that if I simply put these metals in water, it would literally explode and react violently. Okay, so what happens here? I'm gonna let me finish this. The way you read this is you got the greater than symbol. So lithium is a lot more reactive than potassium, which is a lot more reactive than barium, etc., etc., etc. And you go down the scale until you get the most unreactive metal, which is gold. Okay. Now all of this is reference. It's a relative scale, and it's relative to water or the proton. It's relative to hydrogen. That's how the reference point is. And so this is going to be important in a second when we start looking at some of these metals reacting with hydrogen. Okay. So the ones in white here, which are bold, they are so reactive. I'm just going to call them M prime. Okay. M prime. These guys in white are so reactive that we actually have to store them in like mineral oil. Can't even store them out in the atmosphere because they're reactive with any moisture in the air. So you store them in oil. So in the presence of water, they will react and they will form M, whatever this metal is, lithium to sodium hydroxide plus hydrogen gas. And it will explode because so much heat is given off, and when it explodes, it's because the heat ignites the hydrogen given off, and boom, you get a nice little explosion. Okay. All right. Now, with respect, starting from magnesium, let me change the color here. Starting from magnesium all the way up to lead. Okay. Magnesium is a lot more active than aluminum, a lot more active than manganese, than zinc, etc., until we get to the lead. Now, those metals, I'm just going to label M double prime. They represent the metals from magnesium to lead. Now, you put those in water, and there's no reaction. Okay, they require a little more vigorous conditions. Normally, what you do is you put an acid in there. And what happens is it will produce the corresponding ionic compound M double prime X, whatever the anion of the acid was, plus hydrogen gas. And in both cases, you do get gas being involved. Okay. All right. Then we have hydrogen, which is our relative, our reference point. And then these metals from copper on up, they're probably not very non-reactive. If I put a little bit of acid in there, hydrochloric acid or something like that, they won't react. I need more vigorous conditions, and I need some very strong acids in there to get those things to react. Okay. Now, remember the question I stated earlier, and I said, well, is the most reactive metal in ionic form? There will be a time where you'll be asking the question and say, is hydrogen, because it's reference to hydrogen, and we're dealing with metals. So I'm not saying hydrogen is a metal, but I'm saying because the water and hydrogen is a relative scale. If we see hydrogen, we have to ask the question: is hydrogen in its most reactive form, and most stable form, which would be a proton? If it's not, if hydrogen is not in a proton or in water form, then there's no reaction. But we'll do some examples of that too. Okay. All right. Because the most reactive wants to be a cation. It wants to be ionic. Okay. And the least reactive, it's a lot more stable, more happy, if you will, in the neutral, as a neutral element. So we are just comparing the metals themselves relative to each other. All right. So check the activity series to see which metal or hydrogen, if the hydrogen's involved, is more reactive. The most reactive wants to be in a compound, an ionic compound. If it's already there, then there's no reaction. And then if it isn't, then we have a reaction, and then we just switch the partners with respect to metals. We put them into ionic form first, the new ionic compound, so that we put them together correctly with the right ratio. Then, of course, we put the formulas in. Okay. All right, and of course the physical states, which, if they are all elements, more likely they're solids, all the metals, unless it's mercury. Then if not, then we got to look at solubility rules, things like that. Put them in the correct physical state. Then, of course, we balance the reaction. All right, let's take a look at this reaction here. What you have is the reaction of zinc nitrate in the presence of sodium. Okay. Well, the first thing we do is we look at the activity series and we compare zinc versus sodium. Find them on the activity series, and here we have, here's zinc, okay, and here's sodium. And so number one says that sodium is a lot more reactive than zinc. Okay. Question number two: is sodium in ionic form? Is it an ionic compound? And it's not. It's an elemental form. Okay, so the answer is no. Then we have reaction. Okay, so we exchange partners. And so since this reaction is going to occur, we need to, let me write that down. We got zinc nitrate, okay, plus sodium, okay. And since reaction occurs, we know that the zinc, which is an ionic form, will be converted to elemental form, okay? Then we got to take what's left and put them in together in the right ratio. Sodium's in group 1, so we know that's a +1 ionic charge. And the nitrates are in -1, right? So direct you to the polyatomic ion table. You can determine is charged right there. Okay, that means I can put the sodium nitrate together as a 1-to-1. And since it's sodium, one of the big four, remember that? Solubility, it is soluble, it's aqueous, okay? And then zinc is solid, okay? That's solid. We know all nitrates are also aqueous, also given to you there. And so now we have the chemical reaction for what we are given. Now we got to balance them. And now at this point, like a double replacement reaction that we talked about a while back, in this scenario, it's best to follow the polyatomic ions right here. So we got 2 nitrates. So we simply just, let me change the color so we follow. We got 2 nitrates going on here. So if I put a 2 right here, that balances my nitrates, but then it kicks up my sodium, no problem. Put a 2 right there and the sodium's taken care of. I got 1 zinc, 1 zinc. I have a balanced chemical equation. Okay, and let's put in the reaction. So here's the reaction, and then the physical states I just talked about. Remember, sodium, part of the big four, no matter what is bonded to sodium, it will always be soluble. And zinc is an element which is a solid. So you got it there. And in this case, it's also balanced, and I suggest, like I said earlier, follow the polyatomic ions, and everything else just falls in place. So the ratio here is 1 to 2 sodiums. Now, what if it was the opposite direction? What if, let me demonstrate that. Let's say we reversed it, meaning that we started off with sodium nitrate and we stuck it in with zinc metal, okay? And the question is, will that reaction occur? Now, if we go through the same process, again, we have that sodium is the most stable. Sodium is more reactive than zinc, okay? Then second question, is the most reactive metal in ionic form? And the answer is yes, it's in the form of sodium nitrate. So what we get here is no reaction, okay? Because sodium is already in the most stable state relative to zinc. Zinc is happy there as in the element, okay? So we get no reaction. So this is simply the reverse reaction. We get no reaction, okay? So what that also means that if you're ever given a reaction that gives you no reaction, well, the opposite would give you reaction. Here's the opposite right here. We just did that, okay? These are related to each other. Same reactants are reacting with each other. The difference is that the most reactive metal in this state is already in ionic form, okay? All right. And of course, it's not going to be 2 nitrates because we know that the nitrates each are -1 and sodium is a +1. Okay. All right. So here we have strontium bromide and aluminum. So identify the metals that you're working with. Okay. And here's aluminum and here's strontium. And so we have that SR is more reactive than aluminum. Okay. Second of all, is SR in ionic form? Okay. Answer is yes. Right there, strontium bromide. Okay. Therefore, NR, no reaction here. No reaction because, again, strontium is a lot more reactive than aluminum, and it's already in its most stable state, okay? Which now, if you do the opposite, meaning that now I take aluminum bromide, and I react that with SR, guess what? Yes, I will get a strontium bromide plus aluminum. Okay. Now you think about this is also if you ever want to isolate certain metals, you know, you always find a metal that if that metal that you're wanting to isolate is an ionic form, you just find a metal that's more reactive than the metal you want to isolate, like strontium, and then you are isolating your aluminum. Okay. All right. And the reaction is spontaneous. You know, it's nothing that you have to add to the reaction. It's a spontaneous reaction and it occurs all by itself. Okay, so the opposite reaction will occur. Okay. Again, simply because strontium is not in its most stable state. For the second example I just did, this is the first scenario. Here's the second scenario. Okay, let us continue. No reaction. All right, now here's the one with we have an acid now. All right, so you know sometimes you see an acid or you may see water. That is referring to hydrogen, which is the relative element all these activity series is based on. Okay, and so the question is yes, okay, because aluminum, let's go get the periodic. Aluminum is right here, hydrogen is right here. So aluminum is a lot more reactive than hydrogen, okay? And in this case, aluminum, and then question number 2, is the most reactive metal, in ionic form, okay? And the answer is no. So that means positive reaction. So aluminum goes to, we're going to generate this hydrogen is going to go back into the elemental form, which is H2. Okay, just no different than the other metals that went back from ionic form to elemental form, except the hydrogen, its elemental form is hydrogen gas, right? All right. And then the aluminum goes into ionic form. We're exchanging places, right? But we need to write it first in ionic form, like we've been doing in the past, so we can put them together properly. And then the chlorides each have a -1. And so I need 3 chlorides for every aluminum ion. So I got AlCl3, okay? And so now I can do a series of balancing. Clear up my mess. I mean, we're do this a couple ways. If I put a 2 here, well, let's work this through here, right? Because if I put a 2 here, that increases my chlorides. The hydrogens get taken care of. Yeah, let's work through this. I can demonstrate something here. Let me clean this up a little bit. Okay, so we have aluminum, HCl, okay, and then we're going to make the hydrogen gas, and then plus aluminum chloride. This is probably something that you would end up with. Now you actually ask yourself, how am I going to balance? Well, this is going to take a little bit of trial and error, okay? This is one of the trial and errors out. We got 2 hydrogens here now. What if I put 2 hydrogens right there? Definitely would take care of my hydrogen, right? We're good to go, right? My aluminums are okay. We're good to go with that. The difference is now we have a problem, okay? Because now we have 3 chlorides and 2 chlorides on the reactant side, 3 in the product side, 2 in the right, and on the left-hand side. Now we have a dissimilar number, right? So what if we find a common number? Again, in this case, the common number is 6, right? So if I put a 2 in front of aluminum, that gives me 6 chlorides. And so what if I replace that 2 with a 6? Okay, that gives me 6 chlorides on the left, 6 chlorides on the right, but it kicked up my hydrogen, right, to 6. All right, no problem. I put a 3 in front of H2, and now my hydrogens are taken care of. And now my aluminums need to be increased by a factor of 2. Okay, and so let's go back and check. We got 2 Als over here. We got 2 Als over here. We got 6 hydrogens on the left. We got 6 on the right. We got 6 chlorides on the left and 6 chlorides on the right. Okay, so we're balanced. And I started off first by putting a 2 in front of HCl to balance my hydrogen. And then from there, it kicked off my chloride, so I needed to find a number, a common number, which was 6, because I had a 2 to 3 ratio difference there, right? So very analogous to what we've been doing before, so I kick it up. Now in the past, this could have been like this, and maybe that was more recognizable when you had a diatomic chlorine, and I could have put a 3 over here, and that balanced at 6, but it's not the case. Okay, this is chlorides, so that 2 just balance out my hydrogens, giving me 2 chlorides, so I have a dissimilar number. Okay, then I use the common number to get the chlorides in check, to get them in the balance correctly. All right, so there you go. Okay, the ratio of aluminum to HCl is 2 to 6. You can see all the different ratios there. Okay, we're from here to here, so 2 to 6 ratio. From the aluminums to the aluminum chloride is a 2 to 2 or a 1 to 1, if you see that. From aluminum to hydrogen gas is a 2 to 3 ratio. Okay, from hydrochloric acid to aluminum chloride is a 6 to 2 ratio, and from hydrochloric acid to hydrogen gas is a 6 to 3 ratio. Okay, and those are the ratios that we could use down the road when we start doing calculations. But we need to make sure that we have a balanced chemical equation, because if we were to do any calculations based on this reaction right here, then our numbers would be totally incorrect. It's just not balanced. All right, so with respect to the similar replacement reactions, you simply just ask, determine which is the most reactive metal. If the most reactive metal is in solid form, then it's already in the most stable state, you get no reaction. If it's no, then you get a reaction, okay? All right, so any questions? All right, well, this is what we did before earlier. We kind of introduced it, where we had 2 soluble, they were aqueous solutions, 2 reactants, and you put them together. And so note here, we had 2 different aqueous solutions, okay, ionic compounds, and we put them together, and then they get just exchange partners. So the A now combines with the Y, and the B now combines with the X, okay, to form the new species. Okay, Now, depending on the solubility of the products, will determine whether the reaction is positive. This one is a positive reaction. Why? Because the way it demonstrates, we look up the solubility of AY, and it turns out that it's insoluble. We have a precipitate. Okay, therefore, we have a positive reaction. If both of them by chance were aqueous, if both were AQ, then we get no reaction. Okay, no reaction. They both are aqueous. Both of the products are aqueous. So for this reaction to proceed, we don't really care about the reactants, okay? What we're concerned about are the products, the solubility of the products. That determines whether a reaction is positive or not. We call this a double replacement reaction, but they're also called precipitation reactions because there's a solid that's being formed. Okay. All right. So solid forms reaction occur. No solid form, no reaction. All right. So we got to make sure we understand the solubility rules so we can determine whether things are soluble or not. We did go in detail about these solubility rules. If you're having challenges with it, let me know. We'll see if we can get it straightened up. We got two columns, basically. Left side is soluble, right side is insoluble. All right, so let's find out. Okay, now there's a couple ways to look at this problem, and you can do it any way you think. Okay, you can recognize right away that first of all, I got two aqueous solutions. Okay, I'm going to exchange partners. I'm going to take the barium and the sulfate, eventually put them together. So I can go very quickly, recognize I got a barium sulfate. I go to the solubility table and I look for sulfate, which is number 5. Okay, normally sulfates, regardless of who they are bonded with, whatever metal they're bonded with, are soluble, except those exceptions of where you got either calcium, strontium, guess what? Barium, silver, and lead. The fact that barium is insoluble automatically says, hey, I got a positive reaction. Okay, so I can continue. If this was insoluble, I'm going to mark it as soluble for right now. If this was insoluble, then I would go to the next one and check its solubility, its next combination, that is magnesium nitrate. Okay, you can see the nitrates are number 3. And the nitrates, regardless of who they are bonded with, are always soluble. So I would put AQ here. If both of these were AQ, there would be no reaction. I don't go any further. I just write N on there. But we got one partnership there that is insoluble. So there is a positive reaction. So we can write the formula. All right. So now when we do that, we need to make sure that we put them together in the correct ratio. So I'm going to write out the new products in ionic form. I'm going to have barium and sulfate. I know that barium is a +2, right? +2 because it's a group 2 metal. And the sulfates, all sulfates have a -2. Right? It's one of the polyatomic ions. Therefore, its formula can be written together as 1-to-1. Right? And I can write it as barium sulfate like so. And since we figured out that this barium sulfate is soluble, I can put the S. Now the next partnership is magnesium and the nitrate. While we have magnesium, which is a +2, it's a group 2A element, metal, will have a +2 when it becomes ionic. And then the nitrates, if you check your polyatomic ion table, you'll find each to have a -1 charge. Right? That means that I need 2 of the nitrates for every magnesium +2 ion. So its formula will be magnesium, parentheses, NO3, 2, and this would be AQ. Because again, nitrates, number 3, are all soluble. All right, once we did that, now we can go back and check and balance it. I think by default, it just balances each other out. Okay, let's change the color so we can check. All right, I got 1 barium, 1 barium. We're good to go. I got 1 magnesium, 1 magnesium. Magnesium's good to go. I got 2 nitrates, which I got 2 nitrates right there. And then I got 1 sulfate, and then just by default, guess what it is? It is a balance. Now, the thing here with respect to balancing, follow the polyatomic ions, the sulfates, the nitrates, etc. And balance those as a whole, as a unit. Yes, if you want, you can sit there and count all the nitrogens, all the oxygens, but it's not necessary. You just follow the polyatomic ions, and by default, everything falls into place. So this reaction proceeds as follows. And it's balanced already. Now, to recognize this type of reaction, recognize that you have 2, most of the time, 90% of the time or more, you have polyatomic ion reactants. That's a good indication that you could probably be dealing with, you have 2 of them, 2 ionic compounds. Note the single replacement. Single replacement, one of these was an element metal. Not here. Both reactants are ionic compounds containing polyatomic ions. Okay, so that's a good indication you might have a double replacement reaction. Right. Okay. All right, let's take a look at this one. All right, so again, before we write everything out, here we got nitrates. Again, the fact that you got nitrates should indicate to you, oh my goodness, no matter whatever I attach it with, whatever cation, I'm going to have a soluble species. Okay, that's why lead nitrate is soluble, because it's attached to nitrate. That means that when I attach it to potassium, it definitely is going to be soluble, because it's a double whammy. Potassium is part of the big 4, and then we got the nitrate, so no question about it. Potassium nitrate is soluble. Now let's take a look at lead and iodide. Okay. Lead's a heavy metal, so that should probably indicate to you we'll have a precipitate. And so I have iodides, which is number 4, which normally are soluble, okay? Normally are soluble, except when they are hooked up with these 3 metals, specific silver, mercury, and guess what? Lead. So definitely we're going to have a positive reaction here, okay? So I just went through the preliminaries to find out if will I get a product, will I get a precipitate, without having to go through all the steps and write everything out. But here we determine it's going to be a positive reaction, so we're going to write all the steps. All right, lead, in this case, we can pretty much assume when we have a multivariable metal that it's going to stay that same charge before and after, okay? So here we have lead plus 2. And you might say, why? Because the nitrates each have a -1, and there are 2 of them. So there's a total of -2 for both the nitrates, which implies that the lead has to be in +2. Okay? The iodides are a -1 all the time, group 7 element. So that means I'm going to need 2 iodides for every lead +2. And then we have the potassium and the nitrate, which is potassiums have a +1, and the nitrates have a -1, so we can just put those together as a 1-to-1 ratio. So here's lead 2 nitrate iodide plus potassium nitrate, which is aqueous. And the lead iodide obviously is solid. Okay. All right. Now we can do a couple ways. Here I would recommend follow the polyatomic ions. You got NO3. I got 2 of them over here. And so let's follow those and balance those first. Okay, so having 2 here, if I put a 2 in front of potassium nitrate, that gives me 2 nitrates. Well, that increases my potassium content. So I go back to reactants, and if I put a 2 in front of Ki, that balances my potassium. But it also increases my iodide, which is okay because I already have 2 iodides on both sides. I got lead 2 iodide. So my iodides are balanced. And then my lead, got 1 lead in the left, 1 on the right, I'm good to go. So that is a balanced chemical reaction. Let me clear my mess and put out the better mess, and the better mess. Okay. All right, so that is an example of a positive double replacement reaction. Okay. All right, next one. Same scenario. All right, we're going to anticipate. I got barium nitrate, which automatically, I'm dealing with those nitrates, no question about it. Nitrates always soluble. So the new combination barium nitrate makes it soluble. Okay. And then silver chloride. Well, no. We're going to have a positive reaction here too. All right, so let's write everything in ionic form. We got barium, which is a +2 species, ionic form. And then the nitrates are a -1. Okay, means we got 2 nitrates. So we got barium, parentheses, NO3 subscript. And then we got the silver, which is always a +1, and the chlorides, which are always a -1. So I can put those together as 1-to-1. Okay. All right. So it takes care of that. Remember to first write them out in ionic form. Now we're going to balance them out. Again, my suggestion is follow the polyatomic ions if you have them. let me change the color here. We got 2 nitrates as reactants. So if we put a 2 in front of silver nitrate, that will balance out my nitrates, right? But that kicks up my silver up to 2. So I only got 1 as a product side. So if I put a 2 in front of silver chloride, that takes care of the silver. But then that kicks up my chlorides to 2, which is not a problem. Why? Because I started off with 2 as barium chloride. And then I got 1 barium on the left, 1 on the right. We got a balanced chemical equation. Okay. And there's another example. Again, the takeaway, quite important, is the fact that one of the products was found to be insoluble. And therefore, that's why we have the reaction here. Okay. Second of all, if you have a positive reaction, put the new reactants, the new products into ionic form first before you put them together as a formula to make sure you put them to, they get put together in the correct ratio. Okay. You know what? I got 211. Why? I'm going to stop it here. Slide 28. A couple more, 2 more things. We'll finish this up for sure on Tuesday. At 11 is like, 15 minutes at the most, 15, 20 minutes, maybe closer to 30 minutes. It's very short. So Tuesday we'll finish up 10 and then definitely knock out chapter 11, because like I stated, it's very